Argonne was actually founded in the early 50s, right after the Manhattan Project. They split out some of the nuclear research. They decided they wanted to do some peaceful nuclear research as well, and they moved it to suburban Chicago. All of the defense stuff went out to the West Coast or to Nevada. Argonne has about 3,000 employees, about half are scientists and engineers. Lamont is about 30 miles outside of Chicago. It's funded mostly by the Department of Energy. Argonne kind of tries to have some big themes, so energy conversion, energy storage, sustainability, national security, and the thing I'm here to talk about is the national user facilities. And so those are all oriented around our science and technology program. So these are some of the user facilities. This is a term that the Department of Energy uses to be these big facilities that cost hundreds of millions of dollars to build. The one near and dear to my heart is the leadership computing. Another big one is the advanced photon source. This is the leadership computing facility. Even though we run big computers, the people are the ones that really make all this work. And so that's a picture of about 3/4 of our staff here. We're located in a building with a lot of the researchers, but we actually run the facilities. This is our kind of circle of life that we call it. We have people who are computer scientists, computational scientists, and the domain scientists are actually out in universities or in small research places. We work with small companies, big companies. And this is something near and dear to my heart. This is our new 10 petaflop computer system. This is why I'm wearing Q. I'm not an escapee from a Sesame Street podcast. This is the Blue Gene Q supercomputer made by IBM. You start out with 16 cores on a chip. You build it into a module, into a compute card, and do a bunch of drawers. The drawers go into a rack. Those racks weigh about 2 tons. They're water cooled, and then you line a whole bunch of them up, and you can get up to a 20 petaflop system. We bought the cut ray version. We have 10 petaflops. So we run at 10 quadrillion floating point operations per second, which is just kind of inconceivable. But we do that with about 100,000 cores for each job, typically. This is what we do. We give it away. We have 3 different allocation programs, and we take these programs and we give people who are all over the world capabilities to run on our system. So we don't use it very much for the people at Argonne. We use it for people all over the world, so they can come and apply for stuff. We have all kinds of different science domains. We do simulations around climate research, around energy sustainability, a lot of material science. Even though this is a very powerful computer, they're struggling right now to simulate 38 atoms of water. So this, it's a very complex thing. These are a couple of examples. One is Pratt & Whitney is designing jet engines using the system. Instead of bending metal and building these things, they try them out in supercomputers, and so they model them. Some people are doing blood flow analysis, so they're able to look at how blood flows through around aneurysms and model how to stop those and maybe how to strengthen arterial walls. Some of the people are mostly at universities. Now, what happens if you don't have access to this? Anybody in this room can apply for time, but you have to have these really large problems. But there are other massively parallel architectures out there. There's cloud computing, there's grid computing, there is the supercomputing system, and there are systems to use all of these. There's everywhere from OpenMP up to web services. OpenMP is something really used in the scientific community, but web services can be used by people who build websites to do these highly distributed things. So the key is that you can learn from these big supercomputers. One of the things we're finding is that we have to keep everything in memory. Tape, nobody really uses anymore. We can't even read off of tape fast enough to make any good use of it. Disk we use pretty much like tape now. We store things out there, and really everything goes into memory. But multi-cores are saving Moore's law. This is the thing that computing is progressing. If you look at the red dots, those are multi-core architecture. So even my 3-year-old PC here has 4 cores in it. This is some of the high-speed computing systems that are around. And so all of these things are joining together to build an ecosystem that people can use to do these really complex problems. And you can use them for anywhere from building really complex websites up to doing high throughput scientific computing. So it's very heterogeneous, very multi-core. It's distributed, it's highly networked, but it's an exciting world. And talk to us at Argonne about how to use these things, and we'll be glad to talk to you.